All right, hi everyone. So this is another example. It is question 28. Let's read the question first. Question 28. Calculate the electric field at the point P in the figure given that the area of both plates to be 0.1 meter square and both plates having a charge of 10 nanocoulomb and minus 10 nanocoulomb respectively. Assume the distance between the plate is much shorter than the length of the plate itself. Now the diagram does not look like this, but it's a bit easier to draw on my board. In the true diagram, the plates are horizontal instead. I made them vertical because at the end of the video, I want to highlight an important concept. So here we have two plates that we consider are much bigger than the length that separates both of them. What that means is the electric field between the plate will be constant. All right, at all points between the plate. If we look at the electric field from the point of view of the positive plate, the electric field E1, and I denoted E1, is going outside, it's pointing outward from the plate. From the point of view of the negative plate, the electric field E2 is pointing inward toward the plate. So we've seen in the summary that the electric field of an infinite plane of charge is equal to sigma, so the surface charge density, divided by 2 multiplied by epsilon 0. Well, in this case, the point P that is mentioned on the diagram is in between the plate. If you look here, both fields, E1 and E2, are pointing exactly in the same direction. In this case, they are pointing in the positive X direction. That means you will need to add both of them. Well, both of them share the same charge. They share the same area, which means that they will share exactly the same surface charge density. So basically the net electric field will be simply this term multiplied by 2. So it will be sigma divided by epsilon 0. Now epsilon 0 is a constant. We simply need to find sigma, the surface charge density. Now remember that the total charge is equal to the surface charge density multiplied by the surface itself. We are told that the total charge on each plate is 10 nanocoulomb. We are also told that the area is 0.1 meter square. So we can isolate sigma. It becomes 100 multiplied by 10 to the power minus 9, or if you prefer, 10 to the power minus 7. That will do the trick also. Now at this point, it's simply a matter of plug and play. We input the value for sigma and we get an electric field of 11,294 Newton per coulomb. All right. Now the point I wanted to mention at the beginning is now we were considering the electric field inside the two plates. But what happens if we want to consider the electric field outside the plate? Let's say we want to know, let's call this one P1 actually, and a point over here P2. Well, if we look, let's say we remove the first plate. The electric field from the second plate will actually be pointing in that direction. So that will be our E2. Now, remember, for this to work, the plate has to be way bigger than the distance at which we are considering the electric field. If we assume that this is the case, well, we have E2 and E1 that are in completely opposite direction, and we know they have exactly the same magnitude, which means that E net over here will be 0. By the same exact logic, if we extend the electric field from the first plate over here, these two electric fields oppose each other, we will get an E net of 0. So we'll learn later in chapter 5 when we will talk about capacitor. This is an interesting property. It's enabled, well, it's a more advanced topic, but it's enabled to filter out the interference, the electromagnetic interference in the air. So it's a really useful concept. So if you ever get that question in a test, remember that the electric field outside the two plate will be 0, at least due to these two plates, all right? Inside the plate, we add both of the electric field, all right? So 0, 0 here, we add the two electric field, and we get this formula over here. All right, so that's it for question 18. Let's move on to the last question of this chapter.